Pues así ganó
Así, ¿no?
Trump, por ejemplo. Así ganó.
De todas formas, de cara al exterior, casi que la imagen como el tipo tiene amplia mayoría. No hay que olvidar.
Okay. Okay. Thank you very much for being here. Today we have a visitor, no online. So it's Alberto Torralba-Torregrosa. He's doing his PhD in the Universitat de Valencia, and you may know him from the JWST collaboration. And today he's going to talk us about the anatomy of an ionized bubble.
Thank you.
Yours.
Okay, yeah, so yeah, that is the title of my talk. So of bubbles, reionization, and extreme galaxies. So first I wanted to give a little bit of an introduction to get everyone on the same page. And I'm sure you have seen this same picture 1,000 times, but well, do this again. And this is basically a summary of pretty much everything that happened since the Big Bang. So starting with the beginning, after the Big Bang, the universe was a soup of hot gas altogether. After it expanded sufficiently to form the first atoms in what we call the recombination. So it was a really hot and ionized soup. It became neutral, suddenly, well, not suddenly, but over a short span of time. And everything was pretty neutral and pretty calm until the first stars and the first galaxies started to form about 0.1 billion years after the Big Bang. And then began the what we call the Epoch of Reionization. So reionization is only the first stars, which were very blue and very hot, emitting a lot of ionizing photons and getting everything hot and everything ionized again. And well, it has remained fully ionized, like the bulk of the bulk of the universe until the present day. And there are a lot of people who are wondering what happened in this region, in this period of the universe called the reionization. And we don't know a lot about that. We know, for example, that the average redshift at which this occurred was somewhere between 7.8 and 8.8. Yeah, or 8 something. And we know that from the CMB, because the analysis of the electron scattering of ionizing photons or the signature that lives in the CMB, this is what it's telling us from the last data. And we also know that the process was mostly complete by redshift 5.5 roughly. And we know that looking at the absorption of the Lyman forest and the most distant quasars. So at such high redshifts, the Lyman forest saturates. So that is telling us that the universe was mostly neutral at that point. So that means that reionization is mostly complete. But there are still a lot of open questions. So the main question being who reionized the universe, or what sources were the main responsibles of causing this. And the main candidates are star formation and AGNs. And well, there are many papers saying one thing and the opposite. For example, and this well, most hydrodynamical simulations that we have so far, like this one, this paper right there, 2020, found that analyzing the production of ionizing photons from star-forming galaxies and AGN, and only AGN, they found that the AGN only started to dominate by redshift 6 in the most optimistic models. And as I said in the previous slide, reionization was already complete by redshift 6, so the AGNs couldn't do a lot to contribute to that. But on the other hand, we were talking about this with Juan Ricardo a few minutes ago, JWST has unveiled a new population, well, new because it wasn't known until now, of what they call little red dots, because they are little, they are red, and they are dots, and which are only like faint quasars, so faint that we couldn't detect them previously. And they seem to be very numerous. Like if you extrapolate the luminosity function that we have for the brightest sources, this seems to be like to 1 or 2 orders of magnitude more numerous than we thought. And the thing is that they also have very blue spectra, so they are very red because they appear to be just obscured, at least in the optical range, in the Western optical, but their UV seems to be very blue. And that is a hint that they might be leaking ionizing photons. So, yeah, this has rekindled a little bit the AGN as like contributors to reionization. Another question is, okay, who reionized the universe? It was like a few very bright sources that did all the job, or maybe it was a lot of numerous faint sources that altogether contributed to reionize the full, the bulk of the AGN. So again, it depends on the model. So if we assume a reasonable escape fraction for faint sources, they can do the job, at least for the ones that we have detected, or if we extrapolate the luminosity functions. But also the most bright sources tend to have also larger escape fractions. So, and we don't know a lot about the luminosity functions of most bright sources because they are more scarce. So they are with the small areas probed by, for example, with JWST that don't have very wide fields yet. We haven't detected a lot of them. They are a little bit not so well studied, let's say. So there are some problems to address these questions. The most important, I think, is being that it is impossible to directly measure the escape fraction of ionizing photons. So the escape fraction is the fraction of ionizing photons that can escape the galaxy as compared to all the photons that are produced. And that is very important to assess because it doesn't matter how bright is your source. If those photons are not able to escape, then they cannot ionize. And it is impossible to measure because since the progress of the reionization was not complete during the reionization, there's a lot of neutral hydrogen gas, and that gas absorbs the UV. So you simply cannot make direct measurements. And another problem is that the main reionizers might be too faint to be detected even for the current surveys that we have. So if those are the responsibles, we will have a bad time finding them. So this was a bit of the introduction. Now I'm going to talk about a particular case of a very strong galaxy. Its name is COLA-1. And well, all the results are presented in this paper that is currently submitted. And yeah, here we go. So let me introduce, this is COLA-1. He's a Lyman-alpha emitter, a redshift 6.6, so that is like in the middle of reionization. This is a big composite image took by NIRCam, 4 filters. I think so. Okay. Never mind. It has its little tail, which I think is very funny, but this is not part of the galaxy at all. This is actually an interloper. This is identified Lyman-alpha emitter of redshift 2. So yeah, but it's not causing a lot of trouble. We can remove it easily.
And it was not the naming because of the.
No, I wish, but no. So it is a Lyman-alpha emitter, and that's how it was detected in 2016, and it is a double peak Lyman-alpha emitter. This is a known X-shooter spectrum. So double peak Lyman-alpha is pretty common at low redshifts because Lyman-alpha is a resonant, highly resonant line. So that means that in the systemic redshift or in the systemic velocity of Lyman-alpha, you have this big absorption that splits the line in two. So the emission is shifted towards the tails of the velocity distribution. So you see this double peak, and that is pretty normal. But the problem here is that, as I said, this is in the middle or late reionization. So the universe was pretty neutral back then. So this is a model about the neutral fraction as a function of redshift. So one is sitting somewhere around here, redshift 6 and something. And yeah, the neutral fraction is pretty high. And by high, I mean that everything above 10 to the minus 5 is pretty neutral. Okay. So we shouldn't be seeing this blue peak because the transmission curves at that redshift, so the redshift column here is a red line, you see there should be 0 transmission in the blue peak. And we should only be able to see these parts. And actually that's what many or all the other Lyman-alpha emitters that we found at such redshift look like. So you see this red peak and then nothing because everything is absorbed. So why is this happening? Well, the main hypothesis is that Cola-1 is living inside an ionized bubble or an ionized region. So everything around this bubble is mostly neutral, but there is a region here, at least in the line of sight, that it is ionized. So the Lyman-alpha line is produced like this, and it travels through the bubble, and if the bubble is big enough, this line can be redshifted and enough to be like shifted away from resonance before it escapes the bubble. So yeah, you can see this double peak, but the condition is that this bubble exists. So is this the case? Well, we'll get to that in a moment, but first I want to introduce the observations that we have for addressing this. This is the JWST Cola-1 field. In this, so this is the full mosaic, and the particular shape of this mosaic is because NIRCam has two models of CCDs, and these are like several exposures in I think it's I don't know how many pointings of NIRCam, and Cola-1 is right there in the middle. Okay, so it is covered by most of the exposures, and it's in the deepest region. So if you go back, we have photometry in 4 broadbands and Grissom spectroscopy in this last one. This covers the rest frame optical of redshift 6.6, and we will be able to see lines as O3, H beta, etc. I will show you. So the Grissom spectroscopy or wide field slitless spectroscopy consists in well, you have your field here. Well, here there's a composite image, but imagine this is only one filter and this one filter, okay? And what you do is you use a Grissom to disperse the light in one direction, in this case, in the horizontal direction, right? So you do that for the whole image, the whole field here. So what you have in the end is a spectrum for every source in your field. That is the main advantage of the Grissom spectroscopy, that you can get a spectrum for everything, and you can perform blind search of sources. What are the problems? Well, the main problem is that all the spectra are blended because it's everything in the same CCD, right? So for example, these two sources are in the same, like, let's say X coordinates. So the spectrum will be blended, will be like, yeah. So for example, yeah, also the source is like covering up all the other possible sources that it has close to it. But well, what we do is to perform a continuum subtraction using just a running kernel, computing the median over the continuum. Well, I'm simplifying it a lot, but that is basically what we do. And you get only the emission line. So this is the map of emission lines of every source. So for example, if this source in this image is like here, you have the emission line here. And you can tell because of the morphology, right? So it is easy to see that this line corresponds to this source, and this line corresponds to this source, right? So it is easy to match because of that. For example, this little thing right here is an O3 emitter, and you can see here the O3 doublet and the H beta line, all these lines correspond to that central object. And well, you can see the morphology already in the spectrum. So that's how we match it. Also with this other source down there, which is also a O3 emitter. And what is really interesting here is that the photometry of this object is heavily contaminated by this other big galaxy. But the spectra is not, because light is dispersed in different wavelengths, right? So although you have a contaminated photometry, you can have very clean measurements of the lights, of the lines. Yeah. So in Oracle 1 field, we have real-time spectroscopy in 2 modules, which module A and module B of JWST that disperse light in opposite directions. So module A, actually I don't think it is like this or the opposite, but anyway, module A disperses in one direction and module B in the other direction. So the reason for taking the spectra in these 2 directions is that you can match the spectra in each direction and like get rid of contamination, right? For example, these are some examples of O3 emitters that we found in this field. So each one, for example, this first one has the module B spectrum, the module A, module B, and this is a combination, the stack of the 2. So you can see a doublet here, O3 doublet with the. We performed a search of these doublets, just like in this image right here, in the emission line image, you run your favorite source extraction software, and you can identify these lines as if it were galaxies. And then you match each line to a source in the actual image. And if you impose a certain wavelength ratio, then you can find all 3 emitters like all these guys that I'm showing right here. So the point of having module A and module B is that you can detect the doublet in both modules. If this was not the right source, maybe you can see the doublet in one module and not in the other. That's why. Of course, we have the module A and module B only for the central regions. For example, for the source, we only have one. So this is a more insecure detection, but you can tell by the morphology. So for example, here module B is in the opposite direction, so it's mirrored. That's why you see that the source is kind of slanted in the direction, the spectrum is in the other direction. And there are other things that can lead us to detect good candidates, such as, for example, here we see 2 clumps, but only one clump has the O3 doublet. So this means that this other clump is actually at a different edge. For example, in this last example, you see many clumps and you see many lines. So this is a very good system, all in the same redshift. But you can also find some contamination. So the main sources of contamination were, for example, pixels. So you can see here a very nice O3 doublet, but it's actually matched to this source that is not really a galaxy. This is a cosmic ray or whatever. Also this one. And for example, you can find something like this. So this is the same O3 doublet, in fact, as in the previous slide, but it is offset. Because in our algorithm, we allow for some offset, but this is too much, right? Like this cannot correspond to this source. In fact, this doublet corresponds to this other source. You see the bad pixel here that was assigned previously. And the difference in being in this source and in this source is just the redshift. So this doublet can be coming from this source at one redshift and from this source at other redshift. So you have to find the right. Well, this is another example of a source which lines that are too bright to correspond to that line. To that image, so this must be contamination as well. So these are the problems, that you cannot really match the lines with the with the images, like in only one way. But anyhow, we did some visual inspections, and this is a fair result. This is a distribution of redshifts of all three emitters that we found, and this is the redshift of color 1. Here is included color 1 as well. So we found there's a slight overdensity here over the median in our mocks in this purple line. But this is a small overdensity. It's not, you see the distribution of objects that we have in our mock in a random direction in the solid histogram. And if we center our mock in object as bright as color 1, you can see that it is a slight overdensity as compared to random, but it is pretty normal. So what the interpretation of this is that the extreme properties that we will see later of color 1 are not due to a big overdensity. So color 1 is in an overdensity, but not too big. So this is a spectrum of color 1 itself. It looks very good because it's very luminous. Very nice O3 doublet, H-beta. We detect HCAM as well. And we also detect, believe it or not, this O3 4364 line. If I show you the 1D spectrum, you can see this is a 3 sigma detection. Not too beautiful, but it's there. And this is an important line because it is very sensitive to temperature and metallicity. So this is the information we have: the spectrum with all the line fluxes and 4 bands of photons. And this is fit to the spectrum that doesn't fit very well. That's another topic. So the first thing that we did is to confirm the redshift of color 1. So this is a Lyman-alpha line, again from a shooter. This is a newer one, a little bit more deep, a little bit deeper, and we obtained the redshift from the spectrum module A, module B. So module A is nailed in the center of the line, and module B has a little bit of an offset, but actually you can see that there is a systemic bias. So the lower the wavelength of the line we measure the redshift, the higher the redshift it is. And this is suggesting that there is a miscalibration in the astrometry of one of the module B, because in Grissom spectrum, what you have is that in the wavelength direction, you also have spatial information. So the spatial information and the wavelength information is degenerated in that x-axis. So if you want to compute very secure or very precise redshifts, you also need very precise astrometry. So with all that, we take this redshift as a fiducial one because it's nails in every line. It's also not very far away from the other. And what this is telling us, going again to this figure of the ionized bubble. So now that we know the exact, let's say, redshift of color 1, we can compute the size of the bubble, or put some constraints of the size of the bubble, because if we say that the Lyman-alpha line is generated as a double peak, but then it travels and at some point it leaves the bubble, at the point it reaches the neutral patch, let's say, then it's absorbed. Everything that is bluer towards the Lyman-alpha line at the point. So if with information of what is the minimum velocity that we can observe in Lyman-alpha, we can determine or we can put some constraints at the size of the bubble, right? Maybe this peak goes like this. This is just a sketch I made. It's not a model, but all this part is absorbed, right? So this is the minimum around -250 kilometers per second. So this corresponds to 0.3 megaparsecs. Actually, in this paper by Mason and Cronke, well, they found that in fact there is a damping wing on Lyman-alpha, so the bubble must be even larger than that. So this maps to models based on the minimum velocity that we can observe. I drew here the color 1 value. They found that the minimum bubble, in fact, has to be around 0.7 megaparsecs. But that is a big bubble. And this is two models, one considering like a perfectly homogeneous bubble, and the other that the neutral fraction depends on R squared. And R squared is chosen because this is a model where the central source is powering the bubble, like it's ionizing from the center upwards, right? So the question now then is color one powering the bubble? Well, the answer is another question, and the question is what is the again the ionizing fraction of color one, right? Like, yeah, as I said, you can be very bright, but if you are not capable of leaking photons, then you cannot ionize nothing. So yeah, we don't know the escape fraction, but we can say something about the leaking. Well, about color one, looking at their measure properties. So that is a summary of everything we measured. I already spoke about the redshift. The second value here is the ionizing photon production efficiency. It is moderately high, so this is compared to other sources in, well, first in the color one field in gray, and to other very similar program of JWST Eiger in darker gray. You can see that it is above average, but it's really nothing too crazy because it's also a very bright source. Then there's a Lyman-alpha escape fraction, and this is very high. So this is 80% Lyman-alpha escape fraction. This is very high even for sources at low redshifts. And actually, this has been proven to be correlated with the Lyman continuum escape fraction. So this is already a hint that this color one might be a powerful leaker. The UV continuum is also very bright, but again, nothing too crazy. And this is indeed an extreme value. The UV slope of color one is minus 3.2. You see that at those redshifts, the average values are something like minus 1 point something. And yeah, so this is way below, like this way bluer than most galaxies or most Lyman-break galaxies. And this has been also been proven to be correlated with the high escape fractions, this very blue slope. We also know that color one is mostly dust-free, and we know that by the Balmer-Lines ratio. So they are compatible with no dust attenuation at all, or negligible at least. Might be also a sign of flicking, depending on who you ask. And also, for example, this could mean that there have been outflows, many things. Well, I didn't say anything about the equivalent weight and metallicity, but this is pretty normal. And the most extreme, in my opinion, thing about color one is its size. It's extremely compact. So the average size of galaxies is around 0.5, 0.6 kiloparsecs. And this galaxy is unresolved in the JWST photometry, at least in our data. And we can only set an upper bound to the size in 0.26 kiloparsecs. And this is very small for how luminous it is, right? Also, the star formation rate is moderately high, but what it is very extreme is this star formation for such a small size, right? And this is quantified in this sigma parameter, which they call star formation rate surface density. Yeah, like the density of star formation in a given size. And this is a strong sign of, a strong sign of a source being a leaker, because every leaker that we found or extreme leaker in the low redshifts, starting with the green piece, the famous green piece at redshift 0 point something, and other extreme leakers and very weird sources that they've been found in the redshift 3, they all have very high star formation surface density as compared to the mean values here in this line. We also compare to all the sources, the other O3 emitters that we detected in the same field. So the lower bound, because as we have an upper bound for the size, we can only set the lower bound for this density, is already very high, right? So this is a strong, especially these three these three values that I highlighted are signs of this being liquid. So another table, these are estimations of Lyman-alpha, Lyman continuum or ionizing photon escape fractions. So again, we cannot measure this directly, but there are a lot of calibrations in the literature with relating that with some of their values, like the Lyman-alpha peak separation. So the closer the peaks are in general, that means more escape. Also, as I said, with the Lyman-alpha escape fraction and with the star formation and surface density and the UV slope, I mentioned all of those. And all these diagnoses are telling us that the escape fraction of this guy is somewhere around 30%, 50%. Well, here it is 80%, 12%. These are marked because these are some extrapolations. Like in this Bailey et al, they have only very low escape fraction sources, and the opposite for this one. So these are a little bit biased, perhaps. But anyhow, it's telling us that the escape fraction must be high. So if we know this, well, if we can put constraints on the escape fractions, we can estimate with a toy model what is the contribution that this source is making to ionize the bubble or the IgM surrounding it, surrounding the source. So this is assuming that Cola-1 has been that bright forever, and it has the escape fraction in the legend, and it's emitting ionizing photons for all these years or mega years, and the shaded region is actually the 0.7 minimum size that we set for the bubble, right, based on the cutoff of the Lyman-alpha profile. So even for escape fractions as low as 20% or 30% that we're seeing, they're nothing crazy according to these calibrations, even though 30% escape fraction is very high as compared to the average. This source is indeed making significant contribution to ionize a region of this size. So maybe we are seeing a very bright source directly contributing to reionization. And and this dashed lines is adding up the contribution of other detected O3 emitters, the neighbors around it. You can see that the contribution of the others is very small in comparison to this central one, assuming again some escape fractions in the literature. So finally, this is a diagram that I like a lot. This is Cola-1 in the middle, and the estimated bubble size. And we found 5 neighbors around Cola-1 at very similar redshift. You can see the redshift here in all the 1D spectrum from the Grissom data, collapsing the 2D spectrum. And it's very interesting because all these 5 candidates are inside or very close to being inside this bubble. In case, well, if this bubble exists, then all these candidates should be very close. So I think it will be very interesting to follow this up because they may show some interesting Lyman-alpha profiles. Like if they are inside the bubble, maybe they also have double peak Lyman-alpha profiles, right? Who knows? I don't know. But that is for sure something worth checking. But that is for future work. So I'm finishing already. I spoke too fast. Okay, that's all right. So there are many open questions, of course. The first one being like, how many sources are like Cola-1? Is there a Cola-2? That is important because, as I said, this is a very strange source, and we haven't found, like, this is the only double peak that we know at redshift 6 or above. And the fact that it is so strange and it is so bright, it might mean that maybe this is just a transient, right? That this is just an event that lasted a couple million years. and that's why we are seeing only that one. But what if every galaxy undergoes this process, but we only see a few because it's a very tiny event? Yeah, so determining how many sources like this is very important to mainly to know if the reionization was affected by these very bright sources. And for example, if there were many bright sources, that would mean faster reionization towards the reionization occurred in the last bins of redshift instead of being a uniform process. Those are only some speculations. So the second open question that I didn't address here is what is the true nature of 401? Because yeah, like what is that? It is a very compact dwarf galaxy with a huge burst of star formation. I actually forgot to include a slide of this, but we discard also in this paper that this is an AGN just based on the width of the boundary lines, because AGN typically show broad components on boundary lines. So we found that if, based on trying to detect wide components, if photon has an AGN, it shouldn't contribute much, like up to 20% being relativistic. So now this is likely star formation. Maybe it's global cluster information, because there are some papers out there that link this very bright bursts to formation of global clusters with high scale fractions. And the other question that I can come up with is what is the exact extent of the bubble? Because I'm here assuming that we have like a spherical symmetrical bubble, but what if this is just an open channel and there's no bubble at all? We only happen to be in the right spot to catch the right angle. And also, what is the composition of the bubble? It is pretty uniform. It is ionized like R squared, like I said before. So yeah, those are a lot of questions are open and yeah, worth exploring. So yeah, this is a picture of my cat for staying until the end, and thank you very much.
Thank you very much. Very nice talk. Questions? Okay.
Too many?
Andres was the first.
Okay, thanks. Thank you, Alberto. Very nice talk. This is far from being my topic, so my question could be very stupid. About the size of this Cola One, this is extremely compact. It's far more compact than, for example, the dwarf spheroidal galaxies that we see in the local group, or even other dwarfs that we see. It is true that it's too big for being a global cluster. And so I was wondering, yes, about the nature. Could you say something about the enclosed dynamical mass by looking at the how, you know, the equivalent width of the lines, or the you know, how, like, can you measure like the velocity and then fit some kind of Jeans equation or something?
The velocity. I don't know a lot about that, but I wouldn't say so. At least with the resolution of this spectrum, but maybe with deeper spectrum we can say something. But yeah, what we saw here is that the nebular lines are pretty much compatible with those Gaussians. So yeah, but no. So I mentioned this not fitting at all fitted spectrum. So here. We don't have I didn't talk about stellar mass because we didn't have a very good estimator of stellar mass. And this is because the models that we use in set fitting tend to not fit very well, especially in this very blue slope. We don't know if actually this is caused by some pitch. This is a real slope, or this is an absorption, or the extreme line that we are not seeing. I don't know. But yeah, you need a very good measurement of the continuum here in the optical, which we don't have for the stellar mass. Yeah, so that's all I can say. And about the size, yeah, so this is UV size. There's another measurement on the Lyman-alpha size, which is a little bit bigger, which you would expect. But yeah, all we know is that it is unresolved, so it's very compact. Maybe that is just like a small region of one galaxy that is outshining the rest. Like that is my guess, for example, but that I don't know.
Thanks.
Antonio and then Elena.
Two quick questions in one.
Okay.
So, could this be a narrow line again? And second, have you already asked for time with NIRCam?
Okay, the new spec, no. And
But you will.
And yeah, it's a good idea. And could it be a narrow line AGN? I actually don't know. Could be. I don't know what are
Because the continuum is so good.
Mhm. So Lyman-alpha line is also very narrow. I don't know how narrow are narrow lines of quasars, but yeah, and
A few hundred kilometers per second, 500, 300.
yeah.
Okay.
Well, then this is
But those are local.
yeah. It could be. The thing is that, well, in any case, it should be compatible with.
You don't have any other lines, right, to measure hardness of the ionization fields.
Lines. Like
Other
like
lines other than oxygen 3 and H beta?
No, only Lyman-alpha. Yeah. Yeah, so I'm not sure, but yeah, narrow. So Lyman-alpha is also very narrow, and I guess this is a very bright source. So if there is an AGN, it also would have a very big black hole mass, and I don't know if that is compatible with a broad line. I'm just saying that we don't know. But it could be.
Yeah.
Yeah, thanks for the talk. I also enjoyed a lot. So this object is has a very blue ultraviolet slope. It has no dust, but it has no AGN. It's very star forming, but still we see it very red. Is it only because of the red shift?
We see it very red.
Red. It's red. No, it's a red object. Is it only because of the red shift that it's so red, or what?
Do you mean in the image, like you can see it visually red?
Mm-hmm.
Well, I think the red colors here is because a boosting of the O3 line. So that's why
Okay.
you see this red, that it doesn't correspond really to a red slope. It's just because you have.
Okay, it's the O3 episode. Okay.
But yeah, you have this color.
Okay.
It's so red.
I see. And another question, you mentioned that you summarized it very briefly how you remove the continuum, but I guess that's really important to the contaminate and to be able to measure properly the emission lines and then to recover any other properties. So do you think could be there any contamination effects that are very difficult to subtract the continuum from contaminating sources, or any analysis that could be affecting how you measure your emission lines?
So I didn't do the part of, that part of the extraction of the emission line image and so on. It could be, however, yeah, I mean, it could be, but I guess it's not too important, especially in these lines, because this is so the equivalent width of this is like 1000 in the rest frame. Well, I'm talking about O3 plus H beta, so it's a high equivalent width. So I wouldn't expect to have a very large systematic error there, at least in the line flux measurements for this object. Maybe for other fainter sources, that is the case. Yeah. Anyway, the optical lines here, the O3, for example, is pretty normal for such a bright source. So it's nothing like that is not the crazy part of this source.
Okay, thank you.
Ricardo and then Alejandro.
Thank you very much for fantastic talk. This is very impressive. This object is remarkably similar to some wimpy galaxies that we have observed with HST, with COS. So I was wondering, so I'm pretty sure that from the data you have in hand is fully compatible with the starbursting of galaxy. However, from the actual data, you haven't seen any other nebular line like helium-2 or carbon.
No, I
Nothing.
think nothing is detected.
So that goes in the direction of to support the interpretation of starburst in nature, right?
Yeah. Yeah. We don't see. I don't recall what is the extent, like the range in wavelength of the exeter data. But yeah, I don't think it goes so much redder than Lyman-alpha, and yeah, for sure there are no other lines of data in that data.
Okay, and then I think this object calls for MIDI data to get access to
The red part.
the redder part of the CD and try to constrain a little bit more the stellar continuum. And see. So I see that the difference between the predicted and the observed is somehow could this be related with the assumptions of the nebular model, nebular continuum? How have you constrained the nebular model in this using your equivalent weights? So it's self-consistent with the spectrum?
So this is done with the prospector code. And yeah, this is I don't recall the exact model, but yeah, I mean, this is I guess this is highly sensitive to your nebular model, also to the initial mass function that you are putting in. I have seen some papers that they managed to get such loop slopes using radiation bound models. But yeah, I don't know a lot about that. But, the strange here thing is that using the regular models, we didn't dig a lot into that, but using like the most usual models and leaving everything as a free parameter, we can get a good fit here. So.
And related with the environment of these objects. So the objects that you have found around are spectroscopically detected, right? But how about using the NIRCam data alone, can you also identify additional Lyman-alpha galaxies in lower mass? Do you think this is feasible?
It could be. Yeah. We didn't explore that.
I'm remembering some previous work, about these large ionized bubbles that predict simulations that predict that these very luminous Lyman-alpha emitters are surrounded by very faint Lyman-alpha galaxies in the outskirts of this. So basically tracing the limits of the bubble.
Okay.
I was wondering whether this could be also possible to do.
Yeah, I mean, we did the SO3 doublet search just to look for the most luminous galaxies. I don't know if running some photos, codes or something would unveil more galaxies, maybe a couple more. But yeah, that is something that it's worth doing.
There is another test that you can do with the shape of the lines. I mean, if this is a truly giant H2 region at this redshift, so the width of the line of the H beta line and the luminosity should be in a very well defined sequence. We call the L sigma relation, which is followed by any H2 region in the local universe and also H2 galaxies. So I think if you are able to resolve the line, as it seems in this case, the width should be related with the luminosity. It's another test.
Okay.
Hi, great talk, very interesting object. Now I regret never finishing the work that I was doing on this object in 2018 with Jordi in Lancaster for a week or something. I have several questions that were already asked, I wanted like a number for the stellar mass, like something around
Okay, so
10 to the 5, 10 to the 9. What are we
I
dealing?
think the number that this speak was giving was 9.5.
Okay.
Yeah, I wouldn't trust that.
Yeah, it's not 10 to the 5.
Yeah, I know.
So that would be high for a
Yeah.
for a globular cluster.
Ah, yes, yes. Sure.
No.
I was thinking about the width of the lines that people were asking, and I was Googling and measuring by eye, and it seemed, yeah, sorry, that's what I do. I don't know if they are resolved, the lines, because the resolution is, I don't know if you don't remember more about this, but I was looking and it seemed like 3 Armstrong, 3 something Armstrong in rest frame.
Mm-hmm.
So they may not be even resolved. And looking at those, because those are nanometers, what you have there. So it seems, I was looking by eye and it seems like the width is around 30 something.
Yes, I'm not sure. Also, you have this problem of the wavelength direction being degenerated with the spectral. So width of lines in Grissom data is a bit complicated because of that.
Yeah.
Although this is mostly a point-like source. But yes, any shape can affect the line width as well.
So the search for the emitters, I don't know if you did this.
Yeah, well, yeah.
So it was, I'm guessing, like looking for 2 sources separated a reasonable amount in the appropriate direction. No?
Yes. Yeah. So the thing is, you have like this doublet, and you have like you run your source extraction, and you detect those 2, and there's an algorithm that detects that those 2 are at well, first that they are compatible with O3 because O3 has a theoretical ratio of 3:1 flux. So if that is compatible within an error, of course, it tries to match that doublet with some source along this line. And if it finds one, then it computes the redshift and says, okay, this must be a redshift 5. So you have the match of this doublet with this source at redshift 5. And maybe these 2 also match with this at redshift 4. Of course, the line separation is not the same at every redshift, but as we have some uncertainties, you can have that confusion. And we ran an algorithm that produces a pretty big catalog of those, and then we visually inspected all the images. So all the candidates are visually inspected.
Also, another question about technicalities, I guess.
Mhm.
For the equivalent width, I'm guessing you use the broadband image data to get the continuum because there's nothing there.
Yes. Basically, So what we did for the equivalent widths is, so the errors on the equivalent widths are large. We used discrete filters, in fact, to get the continuum, and then extrapolating up to this, considering some task law. So yeah, so that's why I said the errors are large. For the brightest sources, that should be okay, but for fainter or 3 meters, that is, yeah.
Is the tail that we see in the image part of Cola one, or it's something else in the background?
It's a foreground contaminant.
It's not the color.
Yes,
It's not the Cola.
it's not the color.
Okay.
Just another question I forgot to mention. So you have the sizes that you reported. So the upper limit in the radius. This is measured from the UV continuum, right?
Yes.
So have you compared the size of the UV stellar continuum with the nebular size of Oxygen 3, for instance?
We only measured that because it was a last PSF that we.
This is something that is also recurrent in this kind of low mass star bursting galaxies, that the nebular emission, especially in the leakers, is somehow more extended than the stellar continuum. So I was wondering whether this could also add some.
Yeah, I can check, but so I didn't even check because it wasn't resolved this filter. So this one had worse PSF, so I just said, okay, no chances is result in this one.
But in general, is it possible to measure from the spectra, from the 2D
From the,
spectra?
yeah, from the lines on the two spectra, it could be.
Okay.
That's true.
One quick question. What was the transformation rate density? Do you have an estimate?
But it's unresolved, right?
So it's larger.
It's larger than 1.36. Because
Well, this is also very dependent on what calibration you use. So,
because I was wondering, so in cosmic known sources, the production of dust becomes very efficient above certain value. So it would be surprising, or maybe it's normal at this redshift, to have very high transformation rate densities with zero dust.
Mhm.
I don't know what are the implications, but at cosmic noon, when the transformation rate density becomes about
Yeah.
I think it's about 1 or about 1 point something, then the fraction of the luminosity that it's released in the infrared against the ultraviolet rises a lot. There's a study by Irene Shibai recently, and I think it's a follow-up of the MOSDEF survey with James Webb. And so,
but you were talking about, so but that is with dusty sources or like with sources that we already know?
no,
they have dust?
low mass galaxies. I can share the figure. I'm talking about this figure. These are relatively low mass galaxies, but when they go above 1 point something, the fraction of the luminosity that goes out in the infrared against the ultraviolet rises a lot. So the interpretation that they do is that about this value, the production of dust becomes very efficient, and then the sources become opaque. So, but that's why.
Yeah, there is,
but this is cosmic noon. It's not.
yeah, well, yes. So there's a lot in contrast with what we found. Yeah.
So maybe Cola 1 is population 3, and then you don't produce dust about certain value. I don't know.
That would be awesome.
Well, so extinction zero compatible with zero doesn't mean that
No.
there is no dust. So, I mean, I wonder whether if you observe the object with the MIDI, you will get the rise of the
I don't know what are the Balmer ratios for those guys. So they are doing the comparison with the infrared because they can get the infrared. But I don't know if you look at the Balmer ratios, maybe they also, maybe these guys,
yes,
they give you zero obscuration.
Also, the extinction comes from the SED fitting of the 4 photometric data points, right?
No, from
No,
the
From the vibral ratio of the lines. Okay.
So that was my question about how reliable those Balmer lines are. They could affect, because for me one of the most surprising results was that there's no dust.
But H gamma was a 3 sigma detection, right?
H gamma is the O343, the third O3 line. Let's say it's a 3 sigma detection. H gamma, I don't recall the. Huh? It's better.
It's better. Okay.
Okay, so any more questions? Or?
Poor guy, let's say.
Let's release him. Thank you. It means
Extensión, que no haya extensión.
Tenéis que tomar una.
Ah, vale, vale.
No,